Okay. Yeah. All right. So welcome to the fourth and final lecture of on machine learning methods in atmosphere, ocean, and climate science. I hope the past three lectures were useful. Thanks for listening. Now, as the title says, in this lecture, we'll discuss some creative applications of machine learning in climate science research. Now, I have selected three case studies, three use cases that demonstrate three different approaches or three different ways of using ML in whatever problem you're trying to solve. But that these case studies are by no means exhaustive, okay? I mean, there's some really good work done by Elizabeth Barnes' group at Colorado State University. For instance, Paul O'Gorman's group at MIT, Pierre Gentin's group at Columbia, and Stephen Rasp's group at TU Munich, just on top of my head. So, feel free to read those papers. And I just want to say that I am not able to cover all those use cases in today's lecture. However, if I may just advertise a bit, our group has recently submitted a paper which nicely outlines all the research that's going on in using ML in climate research, how ML is being incorporated into different levels of climate hierarchies. And just to read an excerpt from the introduction section, we write that ML-assisted analyses have begun to pervade practically all aspects of the existing model hierarchy. They are being used to model fundamental partial differential equations and dynamical systems, with some examples, and to model and perform equation discovery for discovering closed form expressions of subgrid scale processes. Some examples for you to explore, and to even full-blown efforts to completely replace complex weather prediction models with a single climate model. Now, in addition to this, we also discuss these issues related to interpretability, for instance, which many of you raised over the past couple of days. I mean, of course, it's important that your ML model is interpretable in a sense that you can ask or you can inquire why you got the output you got. Now, apart from interpretability, there's also this issue of generalizability. We only have present data and, in some cases, past data. We don't know what the future looks like under a warming climate. So we can train the model on present climate data and only expect that it learns, the governing dynamics and predicts and generalizes well over warmer climates, which we don't have any currently we don't have any way to validate. We don't have observations of the future, right? So together, these two issues are quite important in ensuring that your ML models are trustworthy, because as was mentioned in some other talks this week, it is important from a policymaking perspective as well that your models are trustworthy if you want to use them for policymaking, urban planning, and stuff that really matters on the ground level. You want your ML to be trustworthy, which means you want it to be both interpretable and generalizable. Now, the three case studies that we will discuss today are the following. So the first one relates to how we can use ML to develop a new class of data-driven model parameterizations for different subgrid scale processes. And the second is how you can use ML for equation discovery to inquire what the closed form of these subgrid scale momentum fluxes and so on look like. And then third is how ML is being used in weather forecasting, full-blown weather models that were mentioned in the previous slide. Now let's jump in the first case study. And so this would be in the stratosphere, okay? So just imagine the stratospheric winds. You are visualizing the dynamics at height levels 15 kilometer to 50 kilometer in the atmosphere, and you're in the tropics. So if you look at the zonal wind in the tropics, say, you average them over latitudes of -5 to 5 or -10 to 10. And then on top of that, you just zonally average them over the whole latitude circle. So when you look at the time series of those winds, the tropical stratospheric winds, this is the height axis. This is the years from 1979 to 2010. These are the wind wind strengths. This is the wind strength, and this is the pressure height. So you'll see that the tropical stratospheric wind variability comprises of these oscillating positive and negative jets in the tropics. And, they can go from as strong of an easterly jet as 40 meter per second, -40 meter per second, to a westerly jet of up to 40 meter per second. And these propagate from the upper stratosphere down to the lower stratosphere And if you look at the period, these usually have a period of roughly 28 months. And because of this mode of variability is called quasi-biennial oscillations. I think Kannabiran also showed a plot that discussed the QBO. Now, many studies have shown or explored the possibility of QBO impacting tropical convective activity like ENSO and Madden-Julian oscillation, for instance. And this QBO, this alternating pattern of tropical winds, is driven mostly by a mix of waves, Kelvin waves, mixed Rossby gravity waves, internal gravity waves, and so on. And these internal gravity waves are mostly generated via convection in the ITCZ, Madden-Julian, ENSO, etc. And as was discussed this week plenty of times, these waves exist over a whole spectrum of spatial scales. So because of limited model resolution, the whole spectrum of these gravity waves is not resolved in climate models. Okay, so the next best thing you can do is have a parameterization that parameterizes these processes approximately. Now, that's where this study comes in, which was published in GRL last year. This Espinosa et al. Study, which creates a machine learning emulator to emulate gravity wave parameterizations in intermediate complexity models. Okay, now this emulator is called WaveNet. Okay, so this emulator is called WaveNet, and what it essentially does is it trains on a parameterization, an existing gravity wave parameterization, and then it emulates that in an intermediate complexity climate model with a coarse resolution of 300 kilometer by 300 kilometer in the tropics. So now, let's just look at the description of the machine learning model first, and let's see, based on what we have learned, can we understand the description. So it uses a vanilla artificial neural net, just a fully connected neural net, not a convolutional net, with 9 layers, 7 hidden, 1 input, 1 output. And then it was trained for 200 epochs, much larger than our 10 epochs that we trained a model for. It has a variable learning rate with a log coarse H error and an Adam optimizer with no regularization, so no dropout, no L2, L1 penalty, and so on. And it uses a minibat size of 1024. So I hope these terms make more sense to you now that we have gone through the whole process of understanding what it all means. So this ANN was trained on the 8099 parameterization. We don't have to go into the details, but this 8099 parameterization generates, so the model was run with this parameterization for 5 years, okay? And then this is the drag that was generated in the stratosphere. So you can see corresponding to the alternating patterns of wind in the tropics, you have these alternating stripes, alternating gravity wave drag in the tropical stratosphere that evolves with time. So this is years. Now WaveNet was trained on this year of data, okay? It wasn't trained for the whole 5 years. It was trained on this second year of data, and it was tested on the other 4 years of data, okay? And if you compare the drag generated by WaveNet for 5 years, you will see similar alternating patterns with similar large-scale structures that were generated by 8099. So that's good. Now, if you compare the difference in the tropics between 8099 and WaveNet, the neural net emulator, you'll see that for the training year, the error is quite low, right? But even for the testing years, the test set, the error is not that bad. I mean, you get these large-scale structures, and then there's some drag. It can do better, of course, but it's not bad. What we have is a functioning emulator that can, replicate the large-scale variability in the tropical stratosphere as produced by parameterizations. Now, similarly, if you look at the the wave drag in the northern mid-latitude stratosphere at 60 north, you'll see the parameterization for the training year generated this drag right here. And then for the other years, you see, again, these alternating patterns reminiscent of the seasonal cycle. Now, what's more remarkable in all this is if you just focus on these small structures here, this disruption here, and this spike here. So WaveNet was trained on just 1 year of data. But then even then, if you look at its performance and compare its performance with the parameterization output for these years when it was not trained on, it gets these distortions in polar vortex variability pretty well. So in a sense that it generalizes to something it was not trained on, and it's performing well in such scenarios. And now another remarkable thing about WaveNet is it was only trained on 1 year of data. So that's 12 months. And QBO is 28 months, right? A period of 28 months. So it was roughly trained on only one cycle of the QBO, easterly or westerly phase, I don't remember, but just either the easterly or westerly phase. And even after that, it generalizes to other phases of the QBO pretty well, right? You get these oscillating patterns with a period of roughly 28 months. So that's pretty amazing. And it provides a proof of concept that, climate models can actually use data-driven parameterizations when trained well. Now, about feature selection, there was a question about feature selection as well on Wednesday, I think. So WaveNet was trained on a total of 8 parameters: horizontal winds, vertical pressure velocity, height, temperature, longitude, latitude, surface pressure. Okay. Now, when all these features were considered in training, so the study quantifies the prediction skill using a R-square score, and the higher the R-square score is, the better the prediction. Now, if you look at the prediction made by WaveNet, or the drag generated by WaveNet, when all the features are included during the training, then you see an impressive skill that goes as high as 0.95. You get a pretty impressive R-square score. Now, the interesting thing is, once you play with the feature set, you start omitting different features and you see how that affects your prediction or emulation. Then you notice two pretty cool things. So if you just consider this dark green curve here, that is, if you train the neural net only on the zonal wind speed to emulate the zonal drag, then I don't know if you can figure out or not, but this green line is almost capturing 96% of the prediction skill of the full model. So even if you take just one relevant feature out of the 8 total relevant features. And on the other hand, if you just see what happened if only V is considered, then you get a very poor prediction skill. Now, likewise, for the meridional direction, this is the total skill in light blue, but then if you consider say, let's say light red first, then it's somewhere here. It's difficult to make out, but the prediction skill is pretty impressive, even after you throw away 7 out of the 8 features. And then if you just consider U as your input feature, then you get almost 0 prediction skill. So, you can play around with what features you get, you want to train your model on, but eventually this makes sense because in the tropics, especially, and even in general, the wind structure determines a lot where your gravity waves dissipate and where they do not, because they provide the critical wind filtering for any gravity wave with a given phase speed, and whenever the phase speed of the wave matches the background flow, it just dissipates the momentum. So the zonal wind determines where your gravity wave dissipates the momentum. Okay, so that explains why just using U also gives you a pretty impressive gravity wave drag emulation. Now, this was all done offline. What happens if you remove the parameterization from the GCM and you replace it with the machine learning model WaveNet? What do you get then? So the next set of experiment in this study was plugging in WaveNet instead of 8099 and then testing it on a 4 times CO2 scenario. So the control run here is the regular amount of CO2, roughly 380 ppm or 400 ppm. And then the second row shows what kind of a QBO you get from the parameterization and WaveNet when you set the CO2 to 4 times the current concentration. So this is the control for parameterization. You get a QBO with a period of 25.8 months roughly with some error bars. And the WaveNet generates a QBO with a period of roughly 27 months with some uncertainty. And now if you look at the 4 times CO2 scenario, the parameterization 8099 generates a QBO, a faster QBO with a reduced period of roughly 18 months with plus minus 5 months of uncertainty. WaveNet also simulates a QBO with roughly 20 months. So it reduces from roughly 27 months to 20 months with an error of 7 months roughly. And likewise, the wind strength reduces from 47.8 to 27.9 in the westerly phase for the parameterization, and likewise, the machine learning emulator also produces reduced westerly and easterly wind strands. So again, it's it generalizes on the parameterized data better. I mean, it is consistent, with the parameterized data better. But then we still don't know, if we can't still be sure that this is how the tropical winds would look like in a 4 times CO2 scenario, because we don't have the observations to validate it. These are just predictions based on approximate parameterizations. Now, the parameterizations are not perfect, of course. So to make this point, I show a plot here, which shows gravity wave excitation. So these are gravity waves excited over 2 mountains. One is the Andes, and then the other is the Antarctic Peninsula. These are one of the key hotspots of mountain wave generation in the planet in general. So what you see here is that these waves are excited over these 2 sources, but they move away from those sources and converge towards 60 south to over the ocean, where there's no land really to excite these waves. And if you look at this animation, which shows how such a wave packet evolves, you'll see that waves excited over Andes, again, propagate all the way to over the ocean, and they dissipate their momentum whenever they dissipate, much away from their source, their region of origin. Now, this points 3 basic skills. This suggests that these 3 basic skills, that of lateral propagation, that the wave is moving away from the source, then refraction, which is its wave number and orientation are changing as it goes away from the source, and then transience, like it has a proper transient evolution, which is it is coherent in time. These 3 properties should be considered by any gravity wave parameterization, but any gravity wave parameterization today does not consider any of these properties. So this is a challenge for future gravity wave parameterizations, that they should include this physics into this. They should take this physics into account when they actually estimate the drag by gravity waves in the atmosphere. So that's where my research comes in. What I've been doing is taking the idea of an ML emulator trained on a parameterization, and I'm extending it to non-local emulators that try to embed this physics in their architecture. So instead of training wavenets on parameterizations, we're training it on high resolution global climate data, global climate data, which is of order 1 kilometer global resolution and resolves the whole mesoscale spectrum. So what you're training your model on is actual fluxes that are generated by physics respecting model, and not just approximations generated by parameterizations. So how do we do that? So the typical way to generate a parameterization is use a columnar approximation. That is, if your wave was created in this vertical column in the climate model, it stays within this vertical column. There's no lateral propagation. And then there's steady state dissipation, which means if the wave is generated right now, it is pretty much dissipated at whatever point it should dissipate right away. There's no transient evolution. So to take care of lateral propagation and refraction, to embed that into the model, what we do is we train not on just 1 column. So typically the approach is to take 1 column of meteorological data like winds, temperature, and so on, and then use that to train on the fluxes within that single column. Okay, so it's a column to column mapping. But then what we're doing is we are moving away from this approach, and we are trying to introduce non-local information while training our ML model. So instead of just 1 column, we are taking the 3 by 3 column or a 5 by 5 column, and then training the ML model to get the fluxes in the center column. And the hope is that that takes into account lateral propagation. So now, as per transients, we are exploring the possibility of using recurrent neural networks, and a special type of recurrent neural network called gated recurrent units, which the diagram is kind of shown here, and it consists of 3 gates, but then essentially it's kind of 2 of these cells put in 1 by 1, which means that we use not just the current state of the atmosphere to predict the momentum flux, but we also rely on the previous state to infer the fluxes in time. And if you do that, then it's kind of taking this wave evolution into account and trying to model that coherentness in time of the generated wave. So schematically, what we're doing is, instead of training, so we are training 3 different neural nets. First, which only considers the data in this vertical column. Imagine the depth of this column. And then you try to, take the 3x3 grid around this point over the Andes with topography, and then, take a 5x5 grid around this point, and then train on this data. And then when we do that, I show the standardized flux here, averaged over some time period, and then the black curve here shows the actual flux that should be generated. And this was derived from error 5. So this is the truth. And then if you just take data over the single point over just one column, then what you get, then the flux you get is shown in blue here, which is much weaker than the flux shown in black curve, right? But then as you introduce more and more non-local information into your neural network architecture, then you see that the predicted fluxes improve significantly, and they try to, or they are starting to look something like the true flux. So which provides evidence that not just for gravity waves, but even for other processes that demonstrate non-local horizontal propagation, this kind of approach will provide better emulation of the required fluxes or whatever quantity you are trying to emulate. So that was it for now about ML parameterizations. Next, we go on to equation discovery. So now we will go from the stratosphere into the ocean. And this section will be based on this paper by Lorenzana and Thomas Bolton, which was published a couple of years ago in GRL. And this is about data-driven equation discovery of ocean mesoscale closures. Now, I don't have to repeat what was said multiple times in this workshop, that mesoscales in the ocean matter, but they're also not very well resolved in the climate models because of limited resolution. And any parameterizations used to represent these mesoscales have some conflicting physical properties, like either they dissipate kinetic energy, or they have spurious feedbacks on the large scale currents, introducing further errors, or they use simple quadratic closures or hyperdiffusion to parameterize the subgrid scale momentum and temperature flux. Okay, so there's problems with the mesoscale representation in current ocean models. So this paper, what it claims is that, or what the idea behind this paper is, given, to quote them, given some spatiotemporal data set of subgrid scale eddy forcing, can you actually uncover the equation that could have produced the data set? So given data, you're approximating the equation, the closed form of the equations that could have produced that eddy momentum flux or eddy heat flux. So if you look at the Navier-Stokes equation and do some rearrangement of the terms, your subgrid scale, if you have your data resolved fully, would look something like this. So bar is a spatial average. Okay, so you take the fully resolved term, you compute this term, advective term, nonlinear advective term, over some spatial scale, and then you average, sort of coarse grain the fluxes by averaging over some pre-decided spatial scale. And then this is so U bar is the average coarse grained U, so that's sort of the background flow, and then that represents the background flux, which would be at a coarse resolution if none of the eddies were resolved. Okay, so this difference quantifies the subgrid scale momentum forcing that you're trying to model. And likewise, this second term here, ST, models the heat flux that you want to model, the eddy heat flux. Now, the paper discusses two approaches. It follows two approaches to model this subgrid scale momentum flux. But we'll only discuss one today, and that's called relevance vector machines, which is actually used to get a closed form solution for the eddy flux. For CNNs, don't do that. But there's a trade-off in this case, because these, as you'll see, perform well, but they don't perform well in online tests. They perform well in offline tests, but not in online tests. But then they are more interpretable, because you can interpret the equations that you get, that the RVMs discover, and you can kind of wrap your head around why it is the closed form. Why does the closed form solution look like this? Convolutional neural nets, as we saw, as you go deeper and deeper into the architecture, your interpretability suffers. So you get many blurred objects, and which you cannot directly interpret. So we'll just stick to RVMs for now, and we'll see an application of CNN in the third case study. So here's what they do. So they have two models, one barotropic model, idealized model, one baroclinic model, integrated at a super high resolution so that it resolves a lot of the scales you want to parameterize or are generally parameterized. So that forms the first step of the process. Generate data, high resolution data that you can test your model on. The second is generate a library of functions. So you start with your basic variables like horizontal winds, U, V, and then create a library. So these limited variables will form a basis of your whole functional space that you're exploring. And then you add other functions of these basis functions like the gradients, ux, uy, vx, vy, uv, uvx, all those functions, gradients and products, all linear combinations into the mix. And then now you train on your high resolution data and try to estimate so you try to estimate which functions best describe your subgrid scale closure. Now they experiment a bit. They started with the basic fields U, V, and then they soon realized that instead of U and V, taking these four functions as basis functions, divergence, vorticity, shearing deformation, stretching deformation, they form a better basis. Okay, so that's all. I mean, they found this after they tried some certain basic functions, and then they realized that the weights were, the weights for U, X, and Vy were probably similar, and the weights for Vx and minus Uy were probably similar. So that gives you an idea that vorticity and divergence probably work better as your basis functions. So once you do that, this forms your basis function, and then you create a whole library of function using, all these variations of these four basis functions. So I don't know what many functions they have, but essentially you compute these functions then using the high resolution data. So if you have divergence, you compute the divergence. If you have vorticity, you compute the vorticity from your high resolution data. And then what you do is you essentially assume your closed form solution to be something like this, like linear combination of all the library of functions that you assume. Okay. And the approach they follow is they assume a prior Gaussian distribution for all these Wi. So there's some mean, and then there's some uncertainty in what these could be. And then you iteratively train your model, like it's kind of a regression-like procedure, as they mention here. And you train the model, and then the model then pops out your optimal Wi's, which suggests what the optimal linear combination of these is. So if your Wi is small, that means the contribution of that particular function is not significant, and then you can kind of ignore it. So yeah, this shows here that once you train, you get mean and variance for your parameters Wi, and then based on that you decide which function matters, which doesn't. So once that's done, so once they follow this approach and train their model on the barotropic idealized simulation, they found that this functional form for the X dimension and the Y dimension works pretty well. So this consists of, your subgrid scale momentum flux in the X direction can be written as a combination of your entropy, the X gradient, or the X gradient of your entropy, and then the X gradient of your vorticity times the shear deformation, and then the vorticity times the stretching deformation, the Y gradient of that. So these were the functions they assumed in the library, and then they got W1, W2, W3, and so on. And then, at some point you have to decide what the threshold is to actually consider that a function is contributing significantly or not. So the way they do that is they start with just one basis function. They assume that this is the closure. Okay, that term alone captures all the variability. But then when you compare the variance of this term to the total variance by all the functions in the library, so in this case they notice that it only captures 20% of the variance. So basically, you're getting a much weaker. So this term does not capture the momentum fluxes in its entirety. So next, they increase the basis. They increase the size of the approximation by considering more functions. So they consider two more functions, this second one and the third one. And then once they do that, they are able to capture roughly 50%, a little more than 50% of the variability. So then they treat this as the subgrid closure for the barotropic model. And likewise, for the bicomponent, you have some similar form with X replaced with Y and Y replaced with X. And if you look at the magnitude of these terms, they're comparable. They have similar order of magnitude. And I mean, they do further statistical analyses, and then they boil this down with some error using relative standard deviation principles to this form. So then this barotropic subgrid scale momentum flux can be written using this library of functions as this. So like a constant, barotropic constant, which is the average of these 6 constants and the divergence term of these 4 quantities. Okay, so then that gives you a closed form solution for your subgrid scale momentum flux. And then they do so for the baroclinic form as well, and find something similar. So the baroclinic subgrid scale momentum flux is a sum of this term and this term. And this term is similar to this term in form, in a sense that it has, vorticity, shear deformation, stretching deformation, and then it has a constant, and then the overall flux is the divergence of this term plus some other term. And you can physically interpret these terms. So you can kind of go back and see how you can interpret these terms, and they do so, but I won't go into those details. And what they found out was that this form that they arrived at was similar to a form they proposed 3 or 4 years back to generate a parameterization. So they didn't use any machine learning; they just started from physical principles. So Lorenzana was a creator, was a collaborator on this study, and she created a parameterization which pretty much used a similar form, which further kind of reassures that the parameterization, the principles the parameterization was based on, was probably correct. But then there are also additional terms that they did not account for. So this gives you a nice interpretable form for your subgrid scale heat flux. Momentum flux. And then they repeat the procedure for the temperature flux, and then they, instead of vorticity and divergence now, they find that your subgrid scale heat flux can be written as a function of your gradients of your velocity. Simply, you don't have to go to entropy and the derivative of your entropy and so on. Now, just to see some results. So these are results for the barotropic case, not for the baroclinic case. And what this figure shows is this mean zonal momentum flux that was in the that was extracted from the high resolution simulation. That's the true eddy subgrid scale flux, which these terms. So it's the x component of this term is plotted right here so the simulation was 10 years long, so it's a 10-year average. And if you compare them with these 3 different cases, first is a parameterization they created in 2017 based on physical principles without any ML. And then this is the relevance vector machine closed form solution that they obtained through regression. And then this is the fully connected convolutional neural net that they used to create the parameterization. Now, if you just look at this, so this is the truth, and this is the emulated version, 3 ways of emulating the subgrid scale momentum flux. You'll see that this structure here is pretty well replicated by RVMs, while the CNNs and the parameterization do not really get the flux in the interior of the domain as well as do the RVMs. And likewise, if you look at the leftmost boundary of the domain, you'll see that the AZ17 parameterization also does not do a very good job of getting the fluxes right in this region. But RVMs also do a poor job. Well, they don't really, it looks different, right? The signs are off. It's positive here, it's negative here. So in this part of the domain, your FCNN, your CNN sort of works better than your RVMs. Now, if you compare the standard deviation in time of these momentum fluxes, this figure shows the standard deviation. And then if you compare the true standard deviation with the standard deviation from the 3 methods, you'll notice that the true standard deviation matches pretty well with the standard deviation of RVMs and the CNNs. So basically your ML emulated variability matches the true variability quite well. But on the other hand, if you compare the parameterization, I'm not sure if I think it's visible here. So the standard deviation in the interior of the domain is pretty weak as compared to the true standard deviation. Now, yeah, these are all RVMs. As I mentioned, RVMs perform in this case pretty well on in offline tests when it's not coupled with the actual code. But then when you actually couple these models to the code and generate the eddy fluxes in real time, it is found, like the study found, that the CNNs perform much better. So even though RVMs, so basically there's a trade-off. RVMs give you an interpretable closed form, but CNNs that don't give you an interpretable closed form, they perform better. And I'm sure this work can guide future research in this area, and the same equation discovery concept can be applied to other physical processes as well, in the atmosphere and ocean and so on. Now this brings us to the last case study, that of ML in weather forecasting, how ML is being used to forecast weather these days. So we'll come back to the surface, no more ocean, and we'll just see the application of ML for weather forecasting. So this, for this case study, I would like to discuss this recently created model, ForecastNet, by this team at NVIDIA. So it's a purely ML-based model that predicts weather and does not have any physics embedded in it. And as we'll see, it still does a pretty good job for short lead times. So the ML technique that powers this ForecastNet weather prediction model, weather forecasting model, is a combination of these two techniques. One is a vision transformer. We have not discussed that yet, but it's one of the relatively newer unsupervised learning techniques, and Fourier neural operators. So it uses a combination of these two techniques to generate really impressive forecasts on 4 to 5 days. So just a brief description of the variables it uses as inputs. So it uses 20 variables as inputs, and the inputs were derived from ERA 5 data, and at the full resolution of 0.25 by 0.25 degrees at a 6-hourly temporal resolution. So these 20 variables at different pressure levels, like one is surface, one is 1000 hectopascal, one is slightly above, and so on. And this is the total column water vapor from ERA 5. So these 20 variables were used all the way from 1979 to 2015 as training data. The next 2 years, 2016 to 2017, were used as validation data. And then the next 3 years, I assume that's all they had, was used for testing the data on out-of-test samples. So in this case, for ForecastNet, the overall procedure from all the way from training your model, inputting the data, all the way to outputting, getting the forecast, consists of 3 stages: the pre-training stage, fine-tuning stage, and the inference stage. Okay, we'll see what this is in more detail. And the model is trained with a variable cosine learning rate for a total of 130 epochs. And again, it's much larger than the number of epochs we used in our tutorials. Now, the architecture of this model is pretty complex, but let's see if we can make sense of it. So yesterday in the CNN tutorial, we looked at a grayscale image can have 1 channel, but a RGB image, a full color image, can have 3 channels, and the total image is a combination of those 3 channels, and each channel captures some feature of the image in one color domain or the other. So ForecastNet, the input of the ForecastNet is designed as such that each of the 20 variables form one separate channel of your input. So it's a 3-dimensional tensor with width, height, and normal width height at 0.25 degree resolution, and 20 channels, 1 for each of the training variables. And so this architecture is a bit complex. What essentially happens is, in CNNs, we ran a convolution through our image, right, with a particular stride, and then we created a reduced feature map using those convolution operations. Here it's different. Here, say this small patch. Here, this whole input is divided into small patches. So say this 2 by 2 patch would form one patch, in this, and then this again, this 2x2 box will form another patch right here. So the whole image is broken into patches, and then these patches are further embedded in they are transformed from, so say it's a 2-dimensional patch right now with certain channels, so it's flattened into a vector, and then it's mapped onto a higher dimension D using a linear projection. So it's okay if you don't understand all of it. I mean, I can't claim to understand all of this as well. So once you perform this linear projection, all this input that you have is sent into something called as an attention layer, which is characteristic of this transformer type of ML model. So, I mean, we won't go into the details for 2 reasons. Firstly, it's a bit complex, so for the interest of time, we'll leave it. And second, even I'm learning about transformers right now, so I don't know the full details. But you're free to read the papers. Now, once you flatten these patches, embed them into a higher, project them onto a higher dimension, and put it into the attention layer, this whole attention layer, these patches, these flattened patches are then mixed around, and the attention layer tracks how these different patches interact with each other. Okay, it's kind of like you're dividing the whole domain into fluid parcels, and then you're tracking how these fluid parcels are interacting with each other. But that's where the analogy ends. Now, in general, suppose you divide this into patches of size p, and suppose you have n total patches. So for n total patches, your attention mechanism uses or has a time computational complexity of O(n) square. Okay, it scales as square of the number of samples. But that's where the Fourier neural operators architecture comes in. So once you replace the normal attention mechanism and you transform everything into Fourier space, your O(n) square complexity changes into, any guesses? O(n). O(n). It's Fourier. Does that give you any hint? Yeah, exactly. It transforms everything from O(n) square to O(n) log n. And that provides you a massive speed up in generating forecasts. Now, once that's done, the output of the attention layer is sent into the linear decoder, which then again maps all these flattened vectors into 2D images. And then you get your final prediction or forecast 6 hours ahead in time. Okay, so 6 hours is the spatial temporal resolution for this. Now, what was I about to say? Yeah, so I mean, this is a complex ML model, right? And it's okay if you don't understand it, but then what we learned over the past 3 days, like ANNs, for instance, they form the building block of many of these layers, like the linear decoder or the linear mappings. So, it's not that what we studied was irrelevant, but even more complex ML models use the simpler models in one way or the other. So, yeah, with that understanding, let's look at the second step. That's the fine tuning. So A and B together form the training part of this more complex model. It's just that they see it as 2 different steps, and rightfully so, because once you put in an input and you generate an output, then you use this output to so this is your input, like your initial condition, and then you use that to generate a forecast at a 6-hour lead time, and then you again use this generated forecast to generate another forecast for the next 6-hour lead time. So then you have one forecast for 6 hours, one for 12 hours. Now you use these together to compute the loss function, and you also put in the true observations at these time steps, and then you use that loss to compute and update your parameters way back using back propagation. Okay, so that's why I guess unlike what we've seen before, now it's using 2 samples to update your parameter weights, your parameters of the model. And the authors claim that this increases the stability of the model, and it somehow increases the accuracy as well. So, and next comes the precipitation. They also forecast the precipitation, but precipitation is not part of this input. So they use precipitation, they use another separate model based on similar architecture, and then they train it separately. And then once your backbone model, which is this model with 20 channels, once that creates an output, they use that forecast, 6-hour forecast, to generate precipitation as a diagnostic. Okay, so it's not a prognostic variable. It's computed later based on the atmospheric conditions. And now comes the inference step, and which is essentially what we discussed. You put an input, you make a prediction, and then you put that prediction into a precipitation model to get the precipitation at that time step. That gives you 21 variables. Now, let's look at how it performs. Okay, so here we have 2 case studies. First is of tropical cyclones, 2 tests, one for tropical cyclones and one for atmospheric rivers. So the first test on the left, this figure shows that the model was, forecast.net was initialized with this initial condition. And then it was used to generate forecasts with, large lead times, 4 days, 5 days, 10 days. And then if you look at a selective forecast, 4 days later, 96 hours, and you compare it with the truth, that is error 5 data, 4 days later, you notice that, just by looking at the image, these wind patterns in the Southern Ocean match pretty well. And then you can probably see this cyclone forming here, which is also there in the truth, in the observations 4 days later. So all in all, the forecast.net demonstrates the capability to spontaneously generate cyclones, even though there were no cyclones in the initialization, in the initial conditions. So that's pretty good. Speaks something about the generalizability of the model, even though there's no physics embedded. Now, likewise, in the Atlantic, there were some depressions in the Atlantic, and then after 4 days, they form into 3 notable cyclones, hurricanes, and then you also get these hurricanes in the truth. So, the forecasts are pretty amazing, I would say. I mean, based on, given that there's no equations being solved here, it's just data. And likewise for atmospheric rivers. So, well, I only learned atmospheric about what they are once when I went to California, because in California, so atmospheric rivers are like huge columns of water vapor rich air that originate in the Pacific, but then they bring huge moisture and precipitation to land, especially the west coast of US when they hit the ground. So otherwise, these atmospheric rivers form up to 60-70% of the total moisture or rains California actually gets in a given year. And otherwise, the conditions are pretty dry. So this test case shows that, okay, so this faint thing is the west coast of US, and this is the Pacific Ocean. And then these are the initial conditions. This is the initial condition that forecast.net was initialized with. And then if you look at the forecast, 36 hours, that's 1.5 days later. And then also 72 hours, 3 days later. And then you compare the forecast by forecast.net with the truth, you'll again see impressive prediction skill. Apart from these small scale structures, which are missing in forecast.net, but are there in the actual observations, the large scale, the gross moisture distribution is emulated pretty well. And similarly, at 72 hours, the large scale structures, these filaments, these fat filaments and these thin filaments are also, they are present in both the observations and the forecast. So to quantify this skill, reduce the error metric to a 1 dimension, they use this quantity called as the anomaly correlation coefficient. It's just a measure of the correlation, the predictive capability of the model. I mean, the exact definition you can, feel free to go into the paper and see for yourself. But the authors, they compute the anomaly correlation coefficient for forecast.net at different lead times. So this is lead times: 0 hour, 48 hours, 96 hours, 148 hours. So they go all the way to 8 days lead time, and then they analyze and compare the anomaly correlation coefficient of forecast.net versus the state-of-the-art weather forecasting system from ECMWF. And what they find is that for short lead times here, the red curve and the blue curve are pretty similar. So for lead times of up to 48 hours or so, the prediction, the forecast skill of forecast-net matches the forecast skill of IFS pretty well. And this is not just because we have reduced the dimension. We looked at the maps, right before this. The maps also agree pretty well, apart from some small scale structures. So, but then of course, yeah, as you go further in time to higher lead times, you'll see that the forecast-net skill starts to drop. But it's still competitive. It's not totally, it's not totally decaying to zero after a couple of days. Now, the most striking thing is the total precipitation TP here. Sorry, so this was the surface wind at 10 meters, the zonal wind at the surface. And this is the total precipitation, which was diagnosed using a different model, if you remember the architecture. So, I mean, the ACC here is pretty amazing because it suggests that for shorter lead times of up to 2 days, the forecast-net, the ML-driven model actually outperforms the state-of-the-art forecasting model, which is shown in blue. Of course, the trend changes for longer lead times, but I mean, this right here, I mean, this shows that data-driven based weather prediction shows promise, and that's all when there's no physics embedded in the model. So I'm sure they're working on embedding physics one way or the other to improve their forecasts. But let's see how this compares with previous studies that focused on deep learning driven weather forecasting. So there was this study, Wayne et al. 2020, which is from the University of Washington, Dale Duran's group, and they use CNNs to make weather forecasts, okay, rather than fancy transformers. So let's just quickly look at what the Wayne et al. Structure looks like what their neural net looks like. So they use something. So they use a number of convolution layers. So as we studied yesterday, we started with a 2D image. We had a convolutional filter, and then we used a pooling layer that reduced the dimension of the image. And then we further applied another convolution filter in red here. And then we further applied max pooling to reduce the dimension further, and so on. So what this Wayne et al. Model does is that it performs that operation to compress or to reduce the dimension of your input image first, and then it does the opposite by using something called as the upsampling. So we use sampling, max pooling to reduce the dimension. Now they further use upsampling to increase the dimension again, and just to make sure that your features are not lost because of this downsampling, they use something called as the skip connection, which borrows features from previous bigger layers which retain more information, and then they use those features, they concatenate or they add it to the upscaled layers here to mix this original upscale information from here with this new upscale information from here with the original information from previous layers. And this kind of an architecture, which first goes down, compresses, and then expands, this is called a UNet architecture. And this was introduced in 2015, and it performs well on medical image recognition and all that. I don't know a lot about that, but yeah, this kind of shape is reminiscent of a U, right? So that's why it's called a UNet architecture, and it's known to perform pretty well. So they use this kind of an architecture to make their predictions and not a transformer. And really quickly, if I just show one sample from their paper, this is a forecast. This is the true temperature on 5th January 2018. And then this right here is the forecast obtained by, starting the forecast at, 10th December. So they initialize their model at on 10 December, and then they let it evolve, and they let the forecast, they generate the forecast for 27 days or so, 25 days. And when you compare the output, the prediction with the actual truth, it's not that bad. I mean, the large scale features are there, even though the wind might be really off. The wind is shown in these black curves, but then the colors show the temperature. So, I mean, it still works pretty well. But then now let's see how it compares with forecast-net. And this curve, this plot shows how they compare with each other. Now the caveat here is the Wayne et al. They also use ERA5 data, the same data as forecast-net, but then they stick to a resolution of 2 degrees instead of a 0.25 resolution used by ForecastNet. So Wayne et al. Is 8 times coarser. It uses more coarser data. That means it has less information about the smaller scales. And so it would probably make more errors when predicting the mesoscales and sub-mesoscales. So the ForecastNet authors, how much time do I have? Oh, time? But we don't worry, we don't care, right? I'm almost there, like 5-10 minutes. I mean, I can stop if it's boring. Okay, yeah.
So did they test it with the same resolution?
Exactly, yeah, that's what we are getting at. So, this bracket, it says 8x quotient. So now what the ForecastNet people do is that they coarse grain their input, and then they now forecast, they make the forecasts at 1/8 of the initial resolution. And when they do that, now they're in a better position to compare, to do a one-on-one apples to apples comparison with the Wayne et al. Model. It doesn't have a name, sadly. ForecastNet is kind of a cool name, right? They should pick a name as well. So, like when you compare the performance of the coarse-grained sort of downscaled IFS and downscaled ForecastNet, and then when you compare it with Wayne et al., you clearly see that. So this is not ACC anymore. This is RMSE. That's a measure of error. So the higher RMSE, the more error you have. The less is your prediction scale. So comparing that, you see that the Wayne et al. 2020 has the highest error. Then there's ForecastNet in the second place, and then they all are still outperformed by the IFS at 2-degree resolution. But nevertheless, I think that's pretty impressive, because there's a lot of missing features here. ForecastNet just uses 20 variables, while IFS uses, I don't know, hundreds of variables in their equations. They have many parameterizations. They have physics embedded. And IFS actually operates at a 9-kilometer resolution, not 30-kilometer resolution, associated with error 5. So this while ForecastNet is trained on 25-kilometer by 25-kilometer data, roughly. So these things add up, and then they contribute to the error that we see here. But remember this curve. Remember this curve. So yeah, that's pretty much it. But like now that we are towards the end, I'd just like to mention some additional sources if you'd like to study ML further when you go back, right? So, I mean, I don't want to overload you with resources, but I'm just suggesting like the books that helped me personally develop a better understanding of ML. So I didn't read this book fully. I just started with it back when I had no idea of ML. And someone suggested that, this is it's actually a 100-page book, which does not have any equations. It intuitively explains everything. And, if you don't want a detailed dive into ML, you can just start with this book and see if it works. But then this is kind of the state-of-the-art book written by some pioneers in the field. And this not just contains the basic concepts and the background information. It also consists treatment on the current research going on in ML. Now, of course, this book is a bit old, so it probably has the techniques that were invented in 2018 or so, but not stuff after that. But still, now the second book, if you want to, I used it to learn PyTorch, how to write ML code in PyTorch. But then I hope that after the workshop, you won't need this. I mean, because I have pretty much, whatever I learned from this book, I've pretty much added to the notebooks. So, the hope is that you won't need this book, but just in case, it does discuss more about tensors and the concept of stride, how the multidimensional tensors are arranged, how PyTorch optimizes some of the functions and all that. So if you're really into that kind of stuff, you can go ahead and read this book or other books that teach PyTorch. Internet sources, again, I have not used all of these. I have looked at this guy's videos to learn how to code PyTorch, how to code models in PyTorch. And I have looked at some of these videos for animations. So a lot of the animations that I showed in the lectures was kind of ripped off from this this page. And it has some, it's not really an ML video, it's more of a, sorry? All good? Yeah, so it's not an ML channel, but then it has some videos on why things work the way they do. Yes, yeah, but then they have many videos on probability, maybe even crypto. I don't know. So then so this is a channel maintained by Andrew Ng, who was a Stanford professor, but now he's, I think, working in a company in Singapore or China. But he had a really good course on Coursera, which I took like 2 years back, and it gives beautiful intuition into machine learning. And again, he works with simple models, nothing fancy, but then that really guides you how to think about intuitively about some of the basic concepts in ML. But I tried to find the Coursera course link. I couldn't find it. I don't know what happened, but just go to his channel. And, I have never seen his videos myself on this channel, but then I looked at it before adding and it looked good. I mean, so if you, want to learn more, it has longer videos. And I don't know why I added this. I forgot, but it seemed like a good channel. And so I thought that, the way I structured the lectures, he had some Jupyter notebooks, I think, with detailed descriptions. So, if you want to learn more, you can explore. If it doesn't work out, then what's the harm? And then this is a YouTube channel which summarizes some of the recent papers in ML. It's a really fast-moving field, and if you really try to keep track of everything's published, you can train everything on a laptop, right? So or on a small cluster. So if you want to keep track of papers, you can. This was suggested to me by a friend. You can look at this now at some point. And I mean, we all are academicians, so we read papers, right? So once you feel confident with the basics, just read papers. I think that helped me a lot, because papers put everything into perspective, which because it's a fast moving field, sometimes books cannot. So I've some papers. This is the paper that discusses variational autoencoders. That's one kind of unsupervised learning used in generative AI these days, like the images we saw in the first lecture, right? They were kind of created with similar kind of models. This is a model, again, that's used for image creation and so on. And then training the model creates instability. So there's some hacks and improvements on this model, something called as cycle GANs. And then transformers were introduced first in this paper. Attention is all you need, a pretty cool title. But then the vision transformers. So this was more used for language modeling. But ForecastNet, as we saw, uses vision transformers because it processes images. So that was introduced in a later paper, which is titled "An Image is Worth 16 by 16 Words." If you want to work with time series forecasting, you can look into another kind of transformers, temporal fusion transformers. And again, if you want to look at more mathematics-oriented paper, how it's being used in numerical computation or climate science, you can look at some other papers. Yeah, thank you. That's pretty much it. And feel free to reach out. Questions? Okay, I'll start from here.
Thank you for a series of talks. So I have a question in the second part, equation discovery using ML. So in that, if we don't know these basis functions for any other type of data sets, so this is a fluid mechanics problem, and these are general quantities in that. So if we don't know these basis functions, so how do we proceed? And in the next slide, you have shown the linear combination. So this, do we give this as input, like we want it in this form, or this is automatically, this automatically comes out like omega square and omega d? So this is my question.
What was the first question? Sorry.
Oh, so the next part was that we get the parameter, the S in form of
the first question. Sorry, the
first question was that if you don't know these basis functions for some problem,
right.
Then how do we approach?
Start with the basics, I guess. I mean, I don't know if you're working with gravity wave drag. Again, I would start with U. I mean, there's some theoretical models that have already preceded this kind of research, right? So I think that can give you an intuitive understanding of what all variables are important. Just like in WaveNet, in the case of WaveNet, we saw U, just training on U or V captures a lot of the variance, right? Similarly, so then that suggests U and its derivatives, V and its derivatives are a nice point to start. But I see your concern. Say you're modeling ice, for instance, then U and V don't make sense. So what do you do in that case? I don't know, maybe ask Anand or, I mean, again, it has to be guided by your understanding of the problem. What variables matter, what don't, latent heat or, ice melt volume or whatever.
Okay.
But yeah, I mean, it definitely helps because this is a dynamical system and we have a properly defined equation. So it makes this easier, definitely. But if it's a more empirical problem, then it becomes tricky. But yeah, try out. I mean, it's all exploratory. I mean, they started with U, V, simple variables, and then they found out that these more advanced, more refined derived variables, divergence, vorticity work better. So start somewhere.
Okay.
And then the second question, what was that? Yeah, this. I mean, so once you create a library of functions, then you are writing your subgrid scale in this form, right? So essentially, once you throw out some terms that you think don't matter, I mean, you choose a threshold. This pops out not a single variable, but a distribution for any variable. So if suppose for any variable, this distribution looks something like this, so then the uncertainty is low because the variance is less. So you will then prefer this over this. So, and then, yeah, you have to do some analyses as to how much variance you want to capture and so on to determine. And then once you throw most of the terms, you naturally get this form. And again, this only captures 50% of the variance. So it's possible you can get more variance by having more terms, but then you have to interpret them. Yeah. There's a question.
Hello, sir. Thank you so much for amazing talks. Sir, just we were discussing yesterday some concepts, yeah, and thinking. Sir, while training that model for good feature recognition, for example, if we are considering a very small kernel size, then it would cost high computational cost. And if we will that keep that kernel size very large, then also this will not be a good training model. Then can we make that kernel size dynamic, that as per the whatever we will require, that we will just optimize its size while the training? Can we make that dynamic size of that kernel?
Yeah, I think I should correct myself. So I went back yesterday and I looked at some studies at UCNN, and there are some studies that actually look at the error and all that as a function of filter size. I've never done that rigorously before. Okay. So I looked at it, and most studies suggest a very small filter. Like 3x3 is ideal, but as you said, then your computation costs are high. But then most of them usually use 3x3 or 5x5 or 7x7, but not more than that.
Yeah.
Even though your image could be large.
No. We were yesterday we were just fixing the one kernel size, and at the process of entire training during entire training, that kernel size was not changing. My question was during the training to just recognize details of the features well. Can we make that kernel size dynamic while the back propagation? Like
I didn't get the last part. Can you change?
Whenever. Like we are calculating error at last, and that back propagating to at that input stage, at the first layer stage. At that time, while selecting the kernel size, can we just replace the new kernel size while the training? Like
while the training, yeah. So you mean if you have, suppose you have 12 channels, then you use different kernel size for different channels?
Yeah.
I'm not sure. I'm not sure if PyTorch by default allows you to do that, but in that case, you will have to write your own functions in PyTorch, but it's definitely doable.
Okay.
But again, don't change the filter size a lot.
Yeah.
Maybe 3 by 3. There's a combination of 7 by 7, 11 by 11, not a lot.
Thank you, sir.
Like in one of the Jupyter notebooks, I use a filter size of 15 by 15. I feel bad about it now.
Yeah, a question from here. Yeah, here.
But at least the feature maps were interpretable. So
How many question here?
Yeah, here.
yeah.
So my question was about the computational cost. This models have this many parameters, this many layers, and very fine resolution. Do they think about computational cost beforehand before building such models? I assume that these are running on supercomputers.
Mhm.
So do they consider that energy consumption?
Yeah. I don't know. I didn't make that model per se, but I do have some answers. For instance, I didn't mention like this forecast net gives you a massive speed up in forecast. So like you can generate one forecast using an ensemble of 100 initializations in just 7 seconds on your laptop. So that's amazing, because otherwise IFS uses big, massive supercomputers and uses hours and hours of time to generate those forecasts. And even then, it just uses 50 ensemble members. So, I mean, ML is giving you massive speed up, and it's also reducing your energy cost, and it's allowing you to generate a forecast on your laptop. If you have a GPU, then even better. But I have this slide which does suggest look at the CO2 emissions during the training process. And I mean, what this suggests is that, GPT-3, ChatGPT, right? So that uses 175 billion parameters, total number of weights, and it like the carbon emission required to train, the total CO2 emitted in training it is like, I don't know, it's a massive times however much we emit in our average lifespan. I don't know, does that answer your question? Like, but I don't know, I'm not sure if ForecastNet uses this much. GPT-3 could be an exception. So I don't know really the details about the training process in those industries.
Yeah, thank you.
Question.
Is that total emissions till now?
I mean, once it's trained, you just use it for inference.
So this is the total emissions created while training GPT-3.
I think so, yeah. Total, yeah. What else could it be?
No, I'm saying it's not that much compared to like this air travel, one passenger, like what?
Yeah, okay. I mean, I don't know what to say. There's also the human life, right? 1 year. So if you multiply, let's take 70 as an average lifespan. So 70 times 5 is 350, but then this is still 500. So it's more than what one human emits in his or her lifetime.
It's not that much.
Well, sure. I'm not saying it's good or bad, because it's possible that once you have a model like this, you can reduce your carbon emission from other sources. I mean,
I'm just wondering why this graphic was created.
What's the point of
I mean, don't you find it interesting? It's it's just a report. I mean, it's not a paper. It was some report by Stanford's HAI lab. So I found it interesting, so I just saved this and I added this. But yeah, like the case of ForecastNet, once you have that model trained, then you can just generate as many forecasts as you want at much less cost. So I'm sure it's not all bad. There's Bitcoin mining as well, right? That also takes a lot of carbon emission, but that's less useful than ForecastNet, I would say. My opinion. So you're saying that if your server is powered by coal, then that's a bad thing, and if it's solar powered, then it's not. Yeah.
Hello.
Yeah.
Sir, while performing that weather forecasting using ForecastNet, whether they have compared with some single GCM or multimodal ensemble.
of
It's a
the-
multi-model ensemble. Yeah, 100 members.
Okay.
Okay, if there are no more questions, we'll end that. Let's thank Aman again.